Well, good morning. And let's refresh the question about the work done by a normal force. First of all, we have to keep in mind normal force is the force. Work done by a normal force is completely different physical quantity. It's a number which can be positive, negative, or zero. And for every force, every time, when we need to calculate work, we need to follow the definition. And the definition includes only three variables: force, displacement, and angle. So we need to see only two vectors: vector which represents displacement, the vector which represents the force, and the angle, which in this case equals 90 degrees. And that's it. That's all I really wanted to see from your pictures. And that's what I saw. You can browse, 70-something pictures. It takes a while to process. So you can find yours, I think. Well, that's not the only slide, of course. There's more and more and more and more. And lots of these pictures missing some elements. For example, right here I can see, well, this picture doesn't show displacement. This picture doesn't show normal force or angle correspondingly, etc., etc. Of course, some pictures are really, really nice. Yeah. Some picture tells you specifically the angle is 90, 90. So I have more. Here we can see displacement, force, and angle. All other elements unnecessary for this particular question, technically. As you can see, some pictures just easier to read, and some pictures really, really hard. So drawing pictures is also a part of practicing. It's an important practice. Nothing else. Just trying to draw an accurate picture takes some experience. And yeah, these are all pretty good ones. And now we didn't finish this. We just started working on this problem. Yeah, you have to figure out when the word work means actually we're doing something together, and when work means mechanical work, when we have to multiply magnitude of a force, magnitude of displacement, and cosine of the angle between force and displacement. In this situation, we have to work it through. Yeah. And all numbers have been already found. So let's do it one more time quickly. We just have to compare different values in the end. So we pushed it, and it stops. The initial velocity points to the right. The initial speed equals 15 meters per second, and the final speed equals 0 meters per second. And well, if we need to compare something to something, we just have to calculate each thing. Kinetic energy. Kinetic energy, by definition, is equal to this product, mass, speed squared over 2. We have to calculate it twice. The initial kinetic energy has to be equal to 40 times 15 squared divided by 2. 40 times 15 squared divided by 2, 4,500 joules. You have to check, because I can make a mistake, because everybody makes mistakes, because mistakes are inevitable and unavoidable, and there is no shame in making a mistake. There is shame, though, in insisting you're right, even if you know already you've made a mistake. That's a shame. Final kinetic energy. of course, is 0. Now we need to compare it to the work done by all forces. And we have found all the work done by all the forces. Let's do it again very, very quickly one more time. Normal force. Normal force itself is not 0, but the work done by the normal force is equal to 0 because of the angle between the force and displacement. Force of gravity, mg, again, is not 0, but the work done by the force of gravity in this case is equal to 0 because the initial height, final height are same. And do we need to include anything related to applied force? That's a yes or no question. Do we have to calculate the work done by applied force? What do you think? Well, you're right. Because there is no applied force acting on the box while the box is sliding. We just gave it a push, and that's it, and we don't touch it anymore. So this is just wrong. Well, there are no wrong questions in general. This is, let's say, not really right question. And there's, of course, most important force, frictional force, kinetic friction, because it's sliding. And if we want to calculate the work done by friction, again, we have to, we don't have to derive that equation every time. We can use it again and again. We have to use that equation, which tells us the work done by friction should be equal to -1 times the normal force times distance traveled by the object. So if we want to use this equation, we need to know the normal force. And we know from the past, for a horizontal object, a horizontally moving object, normal force and force of gravity have exactly the same magnitude. This fact comes from the Newton's second law, which we write relative to the y-axis. And I don't do it again and again and again in all details. I just use the conclusion from our experience. So that's supposed to be m times g. And distance traveled, well, we found it before, but I don't remember the number. So we know that we could calculate the distance traveled if we would use kinematics of this situation. Bless you. Delta x or s or L. In this situation, the magnitudes of all these variables are equal to each other because displacement points to the right. And this is 0, this is 15. We had to use the Newton's second law to calculate the acceleration. And again, the Newton's second law relative to the x-axis told us that relative to x-axis, acceleration and friction both should have negative components. So and we use the definition of coefficient of friction to calculate the acceleration. So force of friction equals coefficient times normal force. And the coefficient is 0.4. And the normal force equals mg. And turns out to calculate acceleration, we didn't have to use the mass because it canceled. Remember, we discussed that. And the magnitude of the acceleration turns out to be 4 meters per second squared. And we use this number here, but in this equation, this number is supposed to represent the component of acceleration which points to the left, so it's negative. And 0 equals 15 squared minus 2 times 4 times distance traveled. And distance traveled, 15 squared over 2 times 4. Okay, let's find it. 15 squared divided by 8, bless you. 28.125 meters. Whew. Now, finally, we can use this number back into the equation for the work done by the force of friction. That's going to be negative 40 times 10 times 28.125. So I got this number. I have to multiply by 40. I have to multiply by 10. Well, I could have multiplied by 400. All right. And that gives me the answer, 11,250 joules. Right? And what did I do wrong? What did I do wrong? I have to check all the numbers now. I did something wrong. I don't know what. Maybe distance. So 15 times 15 divided by 8, 28 times 400. Bless you. Bless all us. I used 40. I used 40 kilograms here, 40 kilograms there. Friction coefficient times normal, coefficient times normal. Of course. Did you find the mistake? I missed the coefficient of friction for the work of friction. And here, it should go right here. Yes. So that's supposed to be additional factor of 0.4. So I gotta do 11,250 times 0.4. And final result is 4,500 joules. Of course, I know what I wanted to get because I knew what we want to prove. And what we want to prove is these numbers are equal to each other. On one hand, 4,500 represents kinetic energy. On another hand, represents the work done. Technically, in physics, when we want to compare something, we calculate change, and change, how did kinetic energy change? Change is equal to final value minus initial, so 0 minus 4,500 joules, negative 4,500 joules. Kinetic energy decreased from something to nothing. And the friction does the negative work, negative 4,500. This minus propagates all through calculations. So, and we can see that, well, technically this is just work of friction, but we can add all those zeros which represent the work of all other forces. And this is a very simple example which proves the very important theorem. For any mechanical situation, when kinetic energy changes, it always equal to the net work done on that object or on that system. Another name, total work done on that object, or in simple terms, the sum of work done by all individual forces. So when several forces simultaneously are acting on an object, every force does some work, maybe positive, maybe negative, maybe zero. If we add all those numbers together, the result has a name, total work or net work. And turns out, no matter what's happening, the net work always equal to the change in the kinetic energy of that system, of that object. If net work is zero, kinetic energy shouldn't change. If net work is negative, like in our example, kinetic energy decreases. If net work is positive, kinetic energy increases, which means the object travels faster and faster. So when we look at the net work done on the system, we can immediately describe what's happening to its motion. Nothing, or slowing down, or speeding up. This is even easier example. But now we just want to apply this new equation, which has a name, Work-Kinetic Energy Theorem, or WKET. Because we know what should happen. From our previous experience, we know that in this situation, when there is no friction, no horizontal forces, and vertical forces cancel each other out, the object should just slide with constant velocity forever. So in this situation, our previous experience tells us that kinetic energy should remain constant, or initial kinetic energy should be equal to final kinetic energy, because there is no friction and vertical forces cancel each other out. Well, but the Work-Kinetic Energy Theorem immediately gives exactly the same result, because as we know, because we just did it, gravity doesn't do any work, normal force doesn't do any work, and if there is no friction, friction doesn't do any work because it doesn't exist. So in this situation, net work done by all forces has to be equal to zero. And if net work is zero, there is no change. If there is no change, it means variable remains constant. Now, let's make things slightly more complicated. Again, no friction in this situation, no friction. But we want to, well, when we have a case of an inclined plane or a ramp, we can roll things down or we can push things up. That's it, right? Without friction, it will move always. Only when friction is present, we may have a situation when object is at rest. And in this case, what do? We pushed and we just need to figure out what's happening to all energies in this situation. So we pushed. If we push just a little, it reaches a certain height, and that's it, and then starts sliding back. If we give a stronger push, it reaches higher height, yeah, higher level. And if we push very strong, it might fly away. So don't do that. Now we have a tool which immediately tells us what should happen to the energies, and that tool has a name, Work-Kinetic Energy Theorem. We just have to apply it, but because it's related to a change, we need to think about two instances or two locations of an object. The first, which we call initial, and the second, which we call final. At the initial location, the object has certain initial kinetic energy. At the final location, the object has certain final kinetic energy. And the change, which is always equal to the difference between final value and initial value, must be equal to the net work done by all forces on this object. So we said net work done by all forces. That means, well, we have to say something about forces. As long as we said the word force, it forces us to talk about forces. Remember that. But that's not a new situation. We've discussed it before. There is force of gravity, normal force, and no friction. So that's it. Now, this is the displacement. And again, if we look at the picture, the angle between normal force and displacement is equal to 90 degrees, which means normal force doesn't do any work, 0. Moving on, there is no friction, so work done by friction is 0. It doesn't exist. Plus the work done by force of gravity. And yesterday we've derived an expression for that. So I don't write zeros, I only write now the term which represents the work done by force of gravity. mg initial minus final vertical coordinates. So what is happening to the kinetic energy depends on what is happening to the height. When height increases, to balance it out, kinetic energy decreases. And when height decreases, kinetic energy increases, which again completely fits our the experience. When it slides down, height decreases, but it travels faster and faster. On its way up, the height increases, but it travels slower and slower. The good thing about this equation, we can rewrite it slightly differently. You see, both parts have something related to the initial location and something related to the final location. So it's kind of convenient just keep everything related to initial location on one side and everything related to final location on another side. And if we do this algebra, kinetic energy final plus mgy final should be equal to kinetic energy initial plus mgy initial. Well, we know that the name for this product, mgy, is gravitational potential energy. In general, in the future, we will learn there are other potential energies. So kinetic energy plus any type of potential energy, and in physics, for any type of potential energy, people use a letter U. This combination, you see, because it is important, it's a part of our reasoning. This combination, of course, now has to be named. And because we're adding energies, we call it energy. Mechanical energy. This is an official definition of a new physical variable, mechanical energy. According to this definition, mechanical energy of an object or of a system is equal to the sum of kinetic energy of that object or a system plus potential energy, well, in our case, but gravitational potential energy. So that's an official definition of mechanical energy. What is happening with my computer today? All right. Something is off. Anyway. By some reason, all handwriting has been shifted to a different slide. There are demons. Well, I'll fix this slide before I post it. So I will move the handwriting back to the original slide. It says, in the absence of friction, like we just proved, mechanical energy initial and mechanical energy final are equal to each other. In physics, when initial value and final value are the same, we call it conservation. So mechanical energy is conserved, doesn't change, remain the same, remain equal when there is no friction acting on a system or in the system. When friction is acting, it changes mechanical energy, actually decreases. Friction is not the only force which might change mechanical energy, but we just stick to friction. And so this statement has been derived from Work-Kinetic Energy Theorem. This statement is derived from the statement above. This statement says if we have a system and we calculate the sum of initial mechanical energy and the work done by friction, that will give us final mechanical energy. Mechanical energy, by definition, is equal to the sum of kinetic and potential. So that's the same equation, just more details. And they all have been derived from Work-Kinetic Energy Theorem. So technically, these are three different forms of the same law. But historically, they also have different names. So when we write it like this, we call it the law of conservation of mechanical energy. When we write it like this, explicitly showing kinetic and potential energies, we call it master equation. And again, when we write it like that, we call it Work-Kinetic Energy Theorem. So now, natural question is, when do we use master equation, or when do we use Work-Kinetic Energy Theorem? Well, technically, it is absolutely up to us, but historically, there is a matter of convenience for most people. When there is no friction, application of law of conservation of mechanical energy makes our calculations kind of easier. Yeah. This term just goes away, done. However, when there is friction, people might sometimes make a mistake. And to decrease the risk of making that mistake, I would recommend using Work-Kinetic Energy Theorem. Again, don't have to do that. Just a matter of convenience. Because again, all those laws represent exactly the same relationship, exactly the same law of nature. Well, we've seen this picture before. Now we just have to apply the law of conservation of mechanical energy, or Work-Kinetic Energy theorem, or master equation to calculate the final speed of this box after it has been pushed for a long period of time. Not just pushed once and then slides on its own. No, we've been pushing it, applying a force during the whole motion. So, friction is not zero. How do we know? We can see and read and recognize numbers and have a short-term memory working. And that forces me, because of my force of habit, using Work-Kinetic Energy theorem, which tells me that change in the kinetic energy of this box should be equal to the net work done by all forces on this box. So on the left-hand side of this equation, I have the difference between the final kinetic energy and initial kinetic energy. The initial kinetic energy is zero because the box starts from rest. And the final kinetic energy is basically what we're looking for. Because if we know that and we know the mass, we can calculate speed. Kinetic energy equals mv squared over 2. Hence, speed will be equal to 2 times kinetic energy divided by m and taking square root of that. That's it. So, in order to calculate the final kinetic energy, we have to calculate the work done by all forces, total. All forces. As long as we said this word, we have to draw the free body diagram to see all the forces. We can see the applied force. There has to be the normal force. There has to be the force of gravity. And there is a force of friction. Friction. Now, for each force, we have to write the term which represents work done by that force. So, without even thinking, I just start labeling all the work done by the normal force, plus the work done by the force of gravity, plus the work done by the applied force, plus the work done by the force of friction. Now, I go back in time and I use the experience we recently had, which tells us normal force in this situation doesn't do any work because the normal force is perpendicular to the displacement. Force of gravity doesn't do any work because of the same reason. So moving on. The applied force. The applied force is constant force. We have to apply a definition of the work done by the constant force, which has 3 terms in it. Bless you. Magnitude, 14. Displacement, well, magnitude of the displacement, 2 meters. And cosine of the angle between the applied force and the displacement. So again, remember, to see the angle, we have to redraw the vectors from the same point. Now we can see the angle between the displacement and the applied force. That angle is 60 degrees. 60. Now, plus, we have to add the work done by force of friction. So it has to be negative. Coefficient of friction, normal force, distance traveled. So, what does it give me? 0 plus 0, that's 0. 14 times 2 times cosine 60 is 14. Minus, and I have to start plugging numbers in. Coefficient, .4. normal force? Say something.
No, I forgot to account for.
Or?
I thought the coefficient of friction was 0.0.
Well, in this situation, oh, sorry. You're right. I thought you've been thinking about the next factor. You should start thinking about the next factor. What's so special about it? Factor, not multiple. The normal force. Is it 20 newtons? Normal force and work normal force, different things. You cannot mix them up, which people do. Normal force is the force, it's a vector, has direction and magnitude. Work done by the normal force is a number. Could be positive, negative, or zero. And this variable, WFN, represents the work done by the normal force, and that is zero. And this variable, F subscript N, represents the magnitude of the normal force. It cannot be equal to zero, but the question is it 20? If you think it's 20, please raise your hand. If you think it's not 20, please raise your hand. So why is it not 20? Because we have to account for the existence of a vertical component of the applied force acting from above, like a hand pushing down, remember? So the normal force, and we cannot forget that experience, we cannot forget that physics. Normal force will be equal to mg plus the vertical component of the applied force. When we push from above, we are increasing the magnitude of the normal force times distance. Okay, keep working. Yeah, that is 0.4. It's on the screen. Now, 2 times 10 plus the vertical component of the applied force should be equal to 14 newtons times what function? Sine, cosine, tangent? Sine. Again, a blast from the past. We have to use the same experience we used before. Sine of 60, and distance is 2 meters. Now we're done. At this point, all we have to do is just take a calculator and finish calculation. This number tells you total work, which in turn will be equal to the change in the kinetic energy, which in turn will be equal to final kinetic energy, which is related to the final speed. Any questions? Yes? Thank you. We can read, right? So what should I change? So when I asked you, is the normal force 20? The answer definitely should have been no, no matter what reason was. Okay, so does it affect anything else? Bless you. No, it doesn't affect anything else. M is here. Yeah. All right. I will switch to the camera in half a minute, so you have only 30 seconds to take a mental picture of this question and start answering. Because there is some general point about this whole topic I want to make. 30 seconds. Well, let's refresh what we've learned. We started from what? We started from learning about distance traveled, average velocity, average speed. I can use any symbol. The light is here. Interesting. So now we cannot trust our eyes. All right. Now, moving on. So what else we've learned? We've learned instantaneous velocity, time, acceleration. We've learned how to read different graphs. Then we moved on to learning about forces acting on different objects. We've learned about the existence of force of gravity, normal force, tension. We learned what net force is and how it's related to mass and acceleration. And now we talk about, probably cannot fit. Now we talk about kinetic energy, potential energy, also known as U, or gravitational potential energy, and work done specific force, net work. And very soon we're going to talk about, very soon, probably today or tomorrow, we're going to talk about even more new physical quantities. We're going to talk about impulse of the force, momentum, and the growing amount of knowledge makes our learning more and more complex. I wouldn't say difficult, I would say complex. And complexity comes not just from the amount of entities. No, complexity always comes from the connections, because all of these variables are connected. For example, we know that acceleration connects everything we can use to describe how things move, and everything we can use to describe why do they move the way they move. And kinetic energy related to work related to forces, and momentum, we will learn, is related to velocities, which way back over here, and impulse of the force is related to the forces, and the time. So this is not a disconnected set of physical variables. This is a very heavily connected set of physical variables. So in a way, when we learn it, we're doing something like this. Yeah. We're adding things we have to hold in our mind at the same time. When it's a 1 or 2, that's manageable. But when we're adding more and more and more and more, it's getting harder and harder to balance them all together, which means only one thing: may require some additional practice. Plus, when we want to solve a problem, like we just did, until we have the problem solved, we never know what would work. So we have to choose a focus on something. Literally, like you in a dark room with a flashlight. You cannot see the whole room. You have to choose a part of a room and try it out. If it doesn't work, you have to shift your focus to a different part of a room of that knowledge, and again, and again, and again. So that means technically you have to keep in mind at the same time all that information. Otherwise, you wouldn't be able to make a shift, which makes many students feel, that's just statistics, that second exam is harder than the first. But now, because you know that might happen, it's all in your hands. If you work through homework problems, again, trying to understand the reason for every step you make, just the number of steps might be larger, yeah? But still, if for every step you make, you know why do that, you should be all set. Now let's see what you said. This is probably the third time we are asking about work done by the normal force, right? Question number 2. And the answer is 0. Because in this situation, of course, if we draw the displacement vector and we'll look at the angle between the normal force and the displacement, the angle will be equal to 90 degrees, which makes the work done by the normal force to be equal 0. Well, we will use this fact very soon, like right now. A block slides down a ramp. We know the coefficient of friction. We know if friction is not very significant, the block will be speeding up. And we have to calculate that speed of the block when it reaches the bottom of the ramp. We can use the lots of things, lots of equations, lots of relationships, so let's use them. Friction is not 0, which means I personally prefer using the Work-Kinetic Energy Theorem. Work-Kinetic Energy Theorem tells me that the change in the kinetic energy should be equal to the total work done on this box by all forces. And again, kinetic energy initial equals 0 because it starts from rest. And kinetic energy final is basically what we're looking for, because if we find kinetic energy final, we can use that number to find final speed now. Forces acting on this box already very well known. That's normal, gravity, and friction. So we should write 3 W's, 3 terms representing work done by normal force, work done by friction, and work done by force of gravity. So the first term is 0. We just answered the question about the work done by normal force. Second term, well, probably we have to write it like 5th time already. Work done by friction is negative, has to be equal to the coefficient of friction times the normal force times the distance traveled by the box. And now we have to add the last term, work done by force of gravity, which should be equal to mg, and the difference between initial and final values of the y coordinate or the height. So keep doing what we're doing. Hence, I want to write both expressions explicitly. Kinetic energy will be equal to mv final squared over 2 minus 0, okay, final minus initial, And on the right-hand side, we can start writing numbers when we know them. Normal force, well, is normal force equal to mg in this situation? That's a yes or no question. What do you think? We have solved this situation before for acceleration, and we know that normal force depends on the angle. It's not mg, it's mg times what? At this point, you have two options. Number one, we have to derive that expression again, and that will take some time. Or you can search in your memory for a memory cell which has that expression in it, which saves time. So what should I write? Sine, cosine, tangent, cosine of this angle. And distance traveled. Well, if it's a 3, 4, 5 ramp, distance traveled from here to there, from the top to the bottom, will be equal to 5. All right. Plus m times 10 times I cannot write any number yet because of missing y-axis. But now when I add y-axis, I still missing one thing. What do I miss? What do I have to add? Just an axis. Every axis has a very special number. Yeah, what number? What number? What is that very, very special number every axis has? What is that number? 0. Yeah, if I ask what that point, you can say origin. If I ask what that number, you should say 0, right? 0. And where can we choose the origin? Where can we choose 0 level? Anywhere. So the rule of thumb is choose it at the lowest location. That makes all heights positive automatically. So now I can write the initial and final. What value, what number should I write for the y initial? Y initial, it starts at the top of the ramp. What number? 3. And final will be 0. But the choice of the origin will not change this difference. We could choose the origin anywhere. We would still get 3 as a result of subtraction of two numbers. So keep going. Hence, mv final squared over 2 should be equal to negative 0.05. Well, I don't have to be so hard on myself. Some people write even worse than I am. So. Mass times 10 times cosine. I don't want to write cosine as a cosine. I want to write a number which represents cosine. This is a 3, 4, 5 triangle. So how can we calculate the cosine of the angle of the incline of this plane? Yes? Way too complicated. That's our ramp, 3, 4, 5. That's the angle. I don't need the angle. All I need is a cosine of that angle. So what do I write? You want to say something? Yes. 4/5 or 4/5. That is correct. Or 0.8, wherever works for you. So this is a cosine. We don't really have to know the angle itself. Plus m times 10 times 3. Now, when you read this problem, you sometimes, not for everybody, but for some of you, your immediate reaction, we cannot solve it because we don't know the mass. But until you solve the problem, you don't know what you need or what you don't need. So you may think that there's some variable which is missing, but you cannot do anything about it. So again, you have to believe that the problem is solvable, that you can solve it, and just move yourself ahead and hope that it's going to work out. Is it going to work out? Can we solve this problem? Yes, we can. Yes. Cannot hear you. Please. Right here. No, I didn't. Thank you. I was so happy that people told me cosine equals 4/5. I immediately moved on. Thank you. That makes whole equation absolutely correct now. And again, can we solve it? This equation has a variable, m, which we don't know. But can we solve it? Yes, we can. Because this variable is a common factor for all terms, so we can cancel it out. And that immediately tells us how to finish this calculation and calculate the final speed. Any questions, please? Now, I don't expect any tricky problems, but in the past, because Webassign randomly chooses values for some things, once or twice it happened that the whole number on the right became negative. That could happen if the coefficient of friction would be too high, like not 0.05 or 1.7, I don't know, by some reason. Well, what would it mean actually, physically? If you want to try to take a square root of a negative number, try. If you take a calculator and you calculate square root of -7, what do you get? What does your calculator tell you? It will tell you something. What does it tell you? Error. It tells error, which means that number doesn't exist in the calculator. But physically, it must mean something very specific. And what does it mean? It means a very simple thing. It means it cannot slide. It means the friction is so strong that the object will not be moving. That's it. That's it. So even if mathematics seems not making any sense, there is physics behind that. Well, that's the opposite problem, so I'm going to do it very quickly. We start at the bottom of the ramp now, right here. And we give a push. So the box now slides up the ramp. And again, as we saw before, if the initial speed is not very high, it might stop somewhere in the middle-ish of the ramp and start sliding back. There is a specific speed we have to supply, so the box would stop right at the top of the ramp. If we gave a push a little bit harder, that would flew over. So that's what we're looking for, that critical speed. And again, because there is some friction, I start from applying Work-Kinetic Energy Theorem. In this case, final kinetic energy is 0. Initial kinetic energy, that's what technically we're looking for. Normal force still doesn't do any work. So our equation can be written like this. Negative mv squared over 2 equals mgy initial minus y final. That's how we always calculate work done by force of gravity. And plus work done by friction, -1 times coefficient times normal force times distance traveled. So keep writing mv initial squared over 2 mg. Now, the initial y coordinate equals to 0, and the final y coordinate will be equal to 3 meters. So 0 minus 3 minus 1 times 0.05 times normal force, still equal to m times g times cosine theta, and the distance traveled. So what does it give me? A negative sine mv initial squared over 2, negative m times 10 times 3, minus 0.05 times m times 10, same cosine, 4/5, and same distance, 5. And again, we can see that we can cancel out the mass from everything. And the good thing is, all terms are negative. If we multiply the whole equation by -1, we make everything positive. That's it. And you can solve it for the initial speed should be equal to square root of 2 times 10 times 3 plus 0.05 times 10 times 4/5 times 5. Done. Any questions? A different type of a situation, a projectile motion. We actually can solve this problem using our previous mathematics. We can write equations for horizontal motion, for vertical motion, yeah, because we've done it before. So we always can check our answer, which we get by using now a different approach. And the new approach, which involves energy and work, gives the answer faster, which is a good thing. So in this situation, a stuntman first travels horizontally, jumps, and lands across the gorge. And we need to calculate the landing speed. Is there any friction involved in this situation? No. How do we know? We can read. It says ignore. If there is no friction, I apply the law of conservation of mechanical energy, normally in the form of the master equation. So no friction. Hence, kinetic initial plus potential initial should be equal to kinetic final plus potential final. And I use a different way to label energies because people also do that. Some textbooks maybe even Webassign. Kinetic potential, kinetic potential. Now I start just replacing each label with the actual expression it represents. Kinetic, mv initial squared over 2. Potential, well, in this situation, that's a gravitational potential energy. And the zero level has been chosen for us, technically, at the bottom of the gorge. So if we choose the y-axis upward, as we should, the initial coordinate will be equal to 70, and the final y-coordinate will be equal to 35. So the initial coordinate equals to 70 meters. Now we move on to the right-hand side of this equation. mv final squared over 2 should plus mg times 35. This, again, is a case when unknown mass immediately getting canceled. And now we can just plug in numbers. 38 squared over 2 plus 10 times 70 should be equal to the unknown speed squared over 2 plus 10 times 35. This equation has only one unknown, so it's easily solvable. The rest is just rearranging numbers, taking a calculator, and calculating the final result. And I have it on the next slide. So I have a strategy, and I follow that strategy. When there is no friction involved, I use law of conservation mechanical energy. When friction is involved in a situation, I use work-kinetic energy theorem. Any questions? All right, so you don't know what's going to happen yet. I'm going to show you. I'm going to do what all physicists and children like to do, break things. This experiment tells us how people came up with the idea of a potential energy. So first we can see the importance of mass. 1 kilogram, the same height. That's why I need this. That's what 1 kilogram did to it. Five kilograms. That's what 5 kilograms did to it. Same height, different mass. Clearly, mass matters. Now we need to use a device which has the same mass, but we could drive it from different heights to see how height matters. And I have a device like that. This one. 4 kilogram weight. All right? This is actually measurable. People used a piece of clay and see how deep it goes, and they were able to relate the initial height and the energy of this weight when it reaches the bottom. You can see with your own eyes how much more energy we store in it by lifting it higher. That's why we call it potential. We store energy. When I move it up, my hand does work, positive work. Gravity does a negative work. I am transferring my energy from me to this object by lifting it higher and higher. More and more energy I'm pumping in it. But when I release it, that all energy which is stored and potentially can be used now is being used. Oh, I love it. M Y, and of course gravity. That's how people came up with the idea MGY, gravitational potential energy. The question here is about conservation. Yeah. In all these experiments, do you think mechanical energy is conserved? So I want to see what you said before we move on. That's a question number 3. Here we says 1. Yes. Well, no, you're wrong. Not much, but still a little. What does crashing mean? Crashing means that different parts of this object, of this can, when they move together, they touch each other and they move relative to each other. And when objects move, surface on surface, what force is acting? Friction. There is internal friction, not big, but still. And that means mechanical energy is changed by work done by friction. However, if I would ask you, is energy conserved? Of course, in that case, you answer always, because energy has many different forms, not just mechanical. There's heat, light, etc., etc. In any process, when we count for all forms of energy, total energy is always conserved. We cannot destroy or create energy. We can only transfer it from one form into another form, from one object into another object. Where did we get energy? We got it from food. Plants, animals, they got it from sun, from the sun. The sun gets the energy from thermonuclear reactions. Thermonuclear reactions happening because it was very heavy and gravitational pull warmed it up. Where did that energy come from? Well, from Big Bang. Where that energy? We have no idea. That's our limit of knowledge, you know. We know it happened, and that's it. Now, it's very important to know that every year we humans consume more and more energy, more and more and more and more, and that's not going to change any soon. And that energy, for decades, and probably for foreseeable future, mostly comes from non-renewable sources. Natural gas, oil, coal. Eventually, we will exhaust all of that. So eventually, we will have to be prepared to use other sources. And whether we like it or not, those sources should also include not just wind or solar, but atomic energy as well. Now, one more question. You can't answer this question yet because you don't know what I'm going to ask you. This is what I'm going to ask you. You can see 2 tracks, number 1, number 2. And I have 2 carts. One will be traveling along path 1, second will be traveling along path 2. And because it's a race, as any race, it might have only 3 possible outcomes. A tie. The cart traveling along path 1 wins the race, or the cart traveling along path 2 wins the race. So the tie can happen. That's why this answer is not even on the screen. So basically, we have to choose between 1 and 2. So what we can see here, they start from the same initial height, and they end at the same final height, which means the initial speed is 0, and final speed has to be the same for both. Speed is the same. This travels shorter distance. This travels longer distance. Basically, that's all we know. And now you can enter your answers. And in physics, if everything goes according to plan, nothing bad happens. We can test our answers experimentally. Close. And go. So, if you thought this card would win, you lost. If you thought this card would win, you won. What does it show us? Well, the question was about time, but the reasoning was about energy and the distance. And again, I just want to draw a path to relate the initial and final speeds. Initial speed, final speed. In the absence of friction, if we apply the law of conservation of mechanical energy, as long as initial height and final height the same for both cards, the final kinetic energy should be the same for both cards, which means the final speed should be the same for both cards. We actually can calculate it as we did before. And by the way, this is an example of a problem about a roller coaster. That's why actually we have to talk about it. If there is a roller coaster and we neglect friction, we can always relate all these variables. Normally, we would have to calculate a final speed if the object starts from rest, or we can calculate initial height if we know the speed at the end, you know. So, but also this experiment tells us that there is basically no direct relation between energy and time. There is no way to make an actual prediction. We guessed. That's it. We may have guessed wrong or correct. Without doing any specific calculation, which we don't know how to do, we could not make a prediction about this experiment. There is no direct connection between energy and time. Well, we have finished everything we had to finish about the energy. Now we're going to start talking about linear momentum as I promised. And I start from the question. That will be the last question for you today, and probably the last problem for us today. What do you think? This is a very common situation when we have an object, something like that, bounce back off a wall. We call it a collision. And the collision takes only a fraction of a second. It happens very, very quickly. Which means, in general, when I throw something, I break everything today. In general, force of gravity might affect the motion of this object. However, if that motion happens very, very quickly, force of gravity doesn't have much time to make any effective influence. So only the wall is acting on the object during this collision. Only the force acting from the wall is responsible for the change in the velocity. The initial velocity points to the left, but when the ball bounces back, the velocity changes to the opposite. It will point to the right. So you will have to calculate the acceleration. That's the initial velocity. And we'll call them initial and final. We could have called them before the collision with the wall and after the collision with the wall, or 1 and 2, doesn't really matter. So how does acceleration point? Well, it has to force the velocity to flip. So the force from the wall on the ball should point to the right. And acceleration due to that force should point to the right. And because we said everything happening so quickly, the collision is ideal, no friction, force of gravity doesn't provide any influence. That's the only force responsible for acceleration, which means that is the net force. Because it's always the case, when only force acts, that force is net force. So we can write F equals ma like this, or we choose positive x direction to the right. So what do we have? We have force has to be equal to m times a Actually, we don't need the force in this question. We just need acceleration. To calculate acceleration, we have to apply the definition of acceleration: final velocity minus initial velocity divided by time. Acceleration will be equal to final velocity. Well, because the collision is ideal, that means the magnitude of velocity doesn't change, speed the same. Only direction changes. So the final velocity points to the right, and the magnitude of that velocity equals 10. Now we have to subtract the initial velocity. And initial velocity points to the left, which means the component of that velocity has to be negative. And we have to divide it by time. That gives us, what does it give us? 20 over 0.1, 2,000 meters per second squared. Or if you want to calculate the force, that would have been 0.1 times 2,000, 200 newtons. This type of a calculation has been done actually by Newton first. Sir Isaac Newton wrote his law initially like this. He didn't like fractions like we do. So this is how Newton wrote his second Newton's law. Not the way we write it today. But turns out this form of the Newton's second law becomes very, very convenient, much more convenient than the contemporary form when we talk about different types of collisions. And if a law has a certain combination of variables, we got to name them. So this product, which is equal to mass of an object times velocity of an object, this product has a name, the impulse, the momentum, the linear momentum, to be exact, the linear momentum. this product, well, technically, this is not the instantaneous force. This is the average force during the collision. Yeah, but the collision takes very short time, so it doesn't really matter. This product of the average force and the time of the collision, this product has a name, the impulse of the force. And now we can write the law which relates these variables. The impulse of the force is equal to change in the linear momentum. This is a Newton's second law in a different form, more convenient, more appropriate for describing collisions. And of course, I have a slide for that. And technically, strictly speaking, now you know everything about impulse and momentum. There are two possible situations which we will explore later. One situation when the net force is not zero, the impulse is not zero. When the impulse of force is not zero, that changes the momentum. That's a Newton's second law again, written in terms of linear momentum. The initial momentum is being changed by the impulse of the force, becomes final. But sometimes the impulse of the force is practically zero or exactly zero. When that might happen? Normally two options. Number one, net force is zero, so there is no force. Number two, the collision happens so quickly, that time is so tiny, this product, force times almost zero, becomes practically equal to zero. And in that case, no matter what's happening inside the system, the linear momentum remains the same. And if something remains the same, we call it conservation. So this is basically the law of conservation of a linear momentum. It says when the net force is zero, or the impulse of the force is practically equal to zero, the linear momentum remains constant, remains the same. And there is another use of this definition. Sometimes it's easier to measure this variable, impulse of a force, and then to use that number to calculate the average force acting on an object during the collision. All right, I'm not going to do that. Oops. So that completes the theory. And that thing should start. All right. Thank you. We are done for today. Don't forget lab number 5 takes place in 1:34 today and tomorrow. Yes, today and tomorrow. Today and tomorrow. Tomorrow is Thursday. Today is Wednesday. On Wednesday. No. I believe you, but I cannot do this one.
An office hour?
They have to take care of first.
Okay.
So today is Wednesday. Everybody who has classes on Monday, Wednesday has a lab today.
Right.
Tomorrow is Thursday. Everybody who has lab on Tuesday, Thursday has lab tomorrow.
So I'll ask you.
See you in 10 minutes.
Okay, yeah.
Yes.
I just have a question. So my lab time is at 6:30 or 6 to 9:30. Is it okay if I go to like the one at 11, or
Why?
I'm not sure if I can make the one